The second talk is on a half light, half matter quasi-particle in van der Waals materials by Professor Vinod Menon. Before to start, I will quickly introduce the Professor Vinod Menon. Vinod Menon is a professor of physics and currently the chair of physics department at City College of New York and doctoral faculty at the Graduate Center of City University of New York. He is a fellow of Optical Society of America and IEEE Distinguished Lecturer in Photonics since 2018 to 2020. He joined Central University New York in fall 2004 as a part of initiative in photonics. Prior to joining Central University New York, he was at Princeton in University 2001 to 2004, where he was the Lucent Well Lab postdoctoral fellow in photonics. He received his MSc in physics from University of Hyderabad and PhD from physics in University of Massachusetts in 2001. He has held visiting position at MIT, Max Planck Institute for Science of Light, and Princeton University. He has also served on the editorial board of Optica and OSA Journal. His currently research interests include cavity QED with two-dimensional semiconductor and organic molecules, and Hamiltonian simulators with light and engineering nonlinear optical materials. We are honored to have you here, sir, and thank you for accepting our invitation. So I would like to hand over to Professor Vinod Menon to share the screen and start the talk.
Give me 1 second. Okay. My slide up. Okay. Okay. Are you seeing it in the presentation mode?
Yes, sir.
Okay. And let me just get my. Okay. Great. Thanks a lot, Kishore, for the kind introduction, and thanks to the IIT Bombay, IEEE Photonics and the Optical Society of America chapters for inviting me to do this on the International Day of Light. It's truly a pleasure to be here. I wish I was doing this in person, but this is as good as it gets these days. Hope all of you are staying safe. First of all, I need to say that it gives me great pleasure to be giving this talk right after Professor Gopal, because I am his junior at University of Hyderabad. And in fact, both of us were at University of Hyderabad at the same time. He finished his MSc a year before me, and both of us probably got all our optics bearings in University of Hyderabad, which had a very strong optics program. So so I'm going to start today's talk, and I'm going to talk mostly about van der Waals materials and some of the work we have been doing recently in the context of strong light matter coupling in these systems. At the very outset, the funding agencies that have made my work possible: National Science Foundation, the Army Research Office, DoD, DOE, Department of Energy, and DARPA, and also some of the centers here at City College. I would also like to mention that I'm happy to take any questions in between if you have any. Otherwise, we can wait till the end. But please feel free to stop me if you have any questions in between. So, what are half-light, half-matter quasiparticles? You probably heard already from Professor Gopal's talk about strong light matter coupling. So I'm going to give still a little bit more introduction on this topic of what it means. So these half-light, half-matter quasiparticles are essentially hybrid states that get created when you have coupling between a material resonance and a photon resonance. And this creates these hybrid states called upper polariton and the lower polariton. And these material resonances can be any of the material resonances that one can imagine. For example, excitons, charge oscillations, lattice vibrations. And a good fraction of the work that Professor Gopal talked about in the context of plasmons comes under the same regime of where you have the charge oscillations strongly coupling to the photon resonance. And of course, you can then couple that to excitons and so on. So we will focus mostly on these three areas, time permitting. We'll see how far we get. But here is some quick history of polaritons. So the idea of polaritons, in fact, if you Google the word polaritons, the thing that tells you is that these are hybrid quasiparticles which have properties of both of material excitations and photons. But the concept of polaritons were introduced for the first time, if you look back in history, in the 50s, in the context of lattice vibrations. And so these are phonon polaritons, if you want to, which are how they are known these days. And it was written in the context of lattice vibrations and coupling of lattice vibrations to optics in ionic crystals and so on. So these are two papers, one from 50 and one from 51. And then about 7 to 8 years later, there were these three papers that came out by Peker, Agranovich, and Hopfield, all three of whom considered what happens to material excitations if the material excitations are excitons, and how they get modified by the electromagnetic radiation. So, and in fact, Hopfield gets credit for using the word polaritons as well. And then about 10 years later, there is the work of Kretschmann and Otto and others on plasmons, where they looked at strong interaction between charge oscillations on a metallic surface and electromagnetic radiation, and ways to see it. So this is where we've these are the three broad kinds of plasmon that we're going to talk about, and just a quick primer on strong coupling. So if I have a material excitation, which is given by this plus minus symbol here, and the material excitation interacts with an electromagnetic field inside a cavity. So I have this resonator, the resonator sitting here. I have the two resonances, the two mirrors, and then the field is sitting inside. And now you ask the question, what happens to the coupling between the electromagnetic radiation and this material excitation? And what you will see is that if the interaction between the material excitation and the cavity photon, which is given by the small g, is greater than the damping rates of both the material excitation and the cavity photon. So you remember, the cavity photon can leak out, the exciton from its excited state can come down. So both of these are the individual damping rates. If these individual damping rates are less than the interaction rate between the two systems, then you enter into the strong coupling regime. And in this case, the Hamiltonian can be given as the sum of the cavity plus exciton plus the interaction term. So this is the term that we are most interested in, and that term is essentially this term here, which tells you the the increase of a photon number and a decrease of an exciton number, and then the other way around. So this is your interaction term, and that when this term becomes important, that's when you get into the strong coupling regime. To make this important, this is the condition that needs to be satisfied. So how do we look at it? So here is your Hamiltonian all written out. If you take this, that's your dispersion of your cavity. The cavity dispersion is got this parabolic shape within a small wave vectors that we are interested in, and then within the same range of wave vectors, if I look at the exciton resonance, you can treat it as a flat resonance or flat dispersion, because you're not coupling to because the wave vectors that we are considering are much smaller than the wave vectors for a much larger the wave vectors that we are using here are much smaller than the wave vectors at which the exciton would actually show some dispersion. So everything we are seeing here, the exciton can be treated as a flat dispersion. You have the cavity dispersion, and now you ask the question, what happens when they get into the strong coupling regime? So here, the Hamiltonian is given by this form, where the off-diagonal terms are the interaction terms, and then these are the resonances of your energies of your exciton and your cavity. And then if you diagonalize this Hamiltonian, you end up getting these two new states, which are depending on the interaction strength, which are given by the plus minus terms, one corresponding to the upper polariton, the plus one, and the minus term corresponding to the lower polariton. And you can describe these polariton states by in a form here, where these terms xk and ck correspond to the fraction of the photon or the exciton in this branch. Or in other words, if I take this branch of lower polariton and I ask the question, what is this? This is a hybrid state of light and matter. But what is the contribution of my matter component here? And what is the contribution of my photon component here? Well, in this particular case, xk will tell you the contribution of the exciton in the branch, and ck will tell you the contribution of the photon. So what you see right away here is that as I go to larger and larger wave vectors, the system becomes more exciton-like. Or in other words, the ck goes down and xk goes up. And if you look at the upper polariton, it's the exact opposite. So you can see how the energy between the contribution of the material excitation and the photon excitations gets shifted as you go in the in-plane momentum. And this is something that is useful to look at nonlinear interactions and so on. So, but from a pedagogical standpoint, this system can be easily modeled with just a coupled oscillator model. So you have two oscillators, A and B, and they are coupled to each other through coupling factor kappa, and they have the spring constants, and you can do what you've learned in your freshman classical mechanics course, identifying getting the normal modes. So this is a nice paper from Lucas Novotny where he where he showed the strong coupling phenomena that one observes in optical systems can be mapped onto a coupled oscillator model nicely, and you can see the new eigenstates that get produced in this system. What one sees is that if I map the two eigenstates of the system, depending on this condition, I can either get the two eigenstates to cross, or I can get them to anti-cross. The anti-crossing only happens if this condition is satisfied. And what does this condition mean? This condition again means that the dissipation in each system must be smaller than the coupling strength between the two the two oscillators. So if you think about like I said, the three quasi-particles that I was just talking to you about, the exciton polaritons are the most have been studied quite a bit lately for various reasons, and I'll tell you that in a second. But the typical signatures that you see are this anti-crossing behavior in the dispersion. So this is the upper polariton and the lower polariton, and the dispersion. And if you do it in time domain, then you can see these oscillations, which are called Rabi oscillations. There is also work on phonon polaritons, which are charge oscillation, which are lattice vibrations that couple to electromagnetic radiations. Now, of course, in this case, the oscillations are lattice vibrations, and so they're usually happening in the infrared part of the spectrum. And then there is Plasmon Polaritons, which are essentially surface plasmons strongly coupling to the or the surface Plasmon Polaritons that get produced because of the coupling between the plasmons, the charge oscillations, and the electromagnetic radiation. So there has been a lot of work in these fields. You heard just now from Professor Gopal about a lot of work on Plasmon Polaritons. One of the faculty at IIT Bombay, Professor Vasa's group has done some really nice work on looking at charge Rabi oscillations in these systems. And so these fields have all been emerging in different directions. Most recently, people have been interested in Plasmon Polaritons from an energy transfer standpoint, phonon polaritons mostly for looking at long-range propagation of phonons and trying to modify the propagation lengths and so on. So really the question comes, polaritons in 2D materials or van der Waals materials, I mean, what is interesting about them? So this is a paper, a review article or a perspective written by Professor Dmitry Basov and co-workers, and they kind of point out the different classes of polaritons that can exist in 2D materials or van der Waals materials. And it's fascinating to me that just from this one class of materials, you can actually see all of these different kinds of polaritons. Or in other words, you can see the Plasmon Polaritons in graphene, phonon polaritons in boron nitride, which is a well-known van der Waals material, exciton polaritons, which will be the I'll discuss in greater length in 2D in van der Waals materials. And there has also been predictions of Cooper pair polaritons and Magnon polaritons in these materials at lower frequencies. So like I said, we'll talk mostly about these. We'll see how far we get. Any questions at this point? If there are no questions, then I'll move forward. I don't see anything in the Q&A. You can also post on the Q&A. So the first paper discussing polaritons was the paper from the paper that introduced the exciton polariton concept was the paper from Hopfield in 1958, where he says, and this is the sentence that one should look carefully: the eigenstates of the system of the crystal and the radiation field are mixtures of photons and excitons. And that is really what gave birth to this whole idea that now you have these hybrid quasiparticles which have got properties of both systems. A lot of work started in the, the work really was pioneered around the late 90s. And then by 2000, everyone was interested in these systems for two reasons. One was the fact that these are composite bosons. So they have half exciton and half photon properties. The advantage being that the excitonic component gives you the electronic response, scattering, nonlinearity, all of those things which photons don't give you. While the photonic component gives you the small mass, the spatial coherence, long range propagation, and so on. So you're really taking the best of both worlds in some ways. And what is more interesting is that you can tune this. So if I stay here at the lowest value of the lower polariton at k equal to 0, the system is very photon-like, which means that the interactions are not going to be that high. If I go to larger values of k, where it becomes more exciton-like, the interactions are going to be much larger. So I can tune my interaction strengths, I can tune how far it propagates, all of this by manipulating the in-plane momentum of the polariton states that I want to look at. The other interesting property of this system is that whatever is happening here inside the cavity is directly related to the in-plane momentum that is inside the cavity is directly related to the angle at which the light is coming out. So, so you can use photons that come out as a signature or something that quantifies what is happening inside the cavity. Now, this is a typical optical cavity. You have a Bragg mirror, so it's a distributed Bragg reflector, two materials with different refractive index stacked together. But what this creates is an electromagnetic field that gets trapped inside the system. And this is trapped in such a way that the antinode is in resonance, is sitting exactly where this material resonance is sitting, or this electronic excitation is sitting. Once that happens, you get into the strong coupling, and if you have the SAT condition that I was telling you earlier satisfied, then you get into the strong coupling regime. So the early interest in all of this was because people were interested in condensation of these things because they behave very similar to atomic condensates, or at least that was a prediction. So the idea here is that you excite polaritons, they scatter, and if you get enough density of polaritons at the minima of your polariton branch, or at k equal to 0, then what you create is a macroscopic coherent state whose emission is coherent, but you have not created a population inversion in this system. So this was very fascinating. So you have a laser, or you have a coherent source of coherent radiation where you don't need population inversion. And so a lot of the earlier work was dedicated towards realizing these polariton condensates, starting with the pioneering work of Claude Weisbuch and others in '92, where they showed the strong coupling. There has been a plethora of work in this topic, both at low temperatures and at room temperature with different material classes. And this is a nice review article that kind of captures everything that happened till 2016. Things have been evolving even after that. So for today's talk, I'm going to focus on 2D materials, especially these transition metal dichalcogenides, which are the molybdenum disulfide, tungsten sulfide, molyselenide, and tungsten selenide. Of course, the 2D material family encompasses everything from graphene, which is a metal, to insulating HBN, to superconductors and semi-metals and things like that. So what makes 2D transition metal dichalcogenides interesting? Well, unlike graphene, which is just made of one sheet of carbon atoms, these materials are actually made of 3 layers of atoms, which makes one monolayer, with the molybdenum or the tungsten atom sitting in the middle, and the sulfur or the selenium or tellurium atom sitting one plane on top and one plane at the bottom. So these 3 atom layer thick layer, it makes one monolayer of the material, and then between these layers, it's held together by a van der Waals force, so it's easy to remove them. Of course, following up on the footsteps of graphene, the way people started working on these is also using the Scotch tape exfoliation technique. So you put a Scotch tape, you peel it off, and you get these monolayer. You can get these a few layers, and then finally monolayer of this material. What is also interesting about these materials is when you go from a bulk to a monolayer limit, you go from an indirect band gap material to a direct band gap material. And that also happens, this also happens that the direct band gap happens at the K point in your crystal lattice and not at the gamma point. And the band, this also introduces some intriguing properties called valley polarization. So all you're doing is you're taking this bulk crystal, you start removing the layers, and once you go down to the monolayer, this thing starts emitting light. And in fact, if you look at the overall, if you look at the photoluminescence from this material, you will see that the difference between one layer and two layer is actually, this is 10 to the 3 compared to this number, about 1,000 times greater than this number. And so this clearly shows that you can get a huge amount of photoluminescence from this material just by going to this monolayer limit, because you're going from indirect band gap to direct band gap. So now comes the question, why do you want to do strong light matter coupling in TMD materials? So for that, a quick primer on excitons. So excitons can be broadly classified into two classes, 1E excitons and Frankel excitons. 1E excitons are those where the electron hole pair are located in two different lattice sites, but are held together by the Coulomb force, and they act like a hydrogen atom. Typically, the hole is heavier than the electron, so the electron is usually going around. And in this case, the Coulomb energy essentially creates a quasi-particle whose energy is less than the actual band gap. So the band gap is here, the exciton energy is lower. And this lowering is the result of the Coulomb attraction. And so you reduce the energy, the overall energy of the system by this Coulomb energy that holds them together. In the case of organic molecular systems, the excitons are different in the sense that the electron and the hole are actually sitting at the same molecular site. So they're very tightly bound. And because they're tightly bound, they have a large oscillator strength typically. They're also shown by these energy levels which sit below the band gap. But in the case of organic materials, you don't talk about a band gap, you talk about molecular orbitals. So this is the highest occupied molecular orbital, and this is the lowest unoccupied molecular orbital. And the exciton that gets produced in these systems is sits again at an energy that is lower than this energy difference between the HOMO-LUMO levels. So these are the two broad classifications of excitons. The typical differences are large exciton radius, small binding energy for the 1E excitons. Because they are delocalized, they propagate long distances ballistically, and they also have small saturation density. You take Frankel excitons, pretty opposite properties. They are localized at the molecular site, very large binding energy, 0.5 to 0.1 eV. You can see here these are barely getting past the room temperature values of 25 MeV. Hopping transport, because they are tightly localized, they cannot go ballistically, so they have to jump from one side to the other. And because these are molecular orbitals and you have several levels available, it's not easy to saturate them. If you think about what happens in the case of these 2D transition metal dichalcogenides, the wave function of the excitons are not actually sitting at one atomic site. It's actually distributed over about 15 atomic sites in radius. So the typical radius is about 1.5 to 2 nanometers for the 1s exciton. And so they are highly delocalized. And if you look at their binding energy, so if you typically take a semiconductor which is bulk in 3D, and you look at its property, you will see that the exciton energy sits here, and then you have a quasi-particle band gap which starts somewhere here, and this is your binding energy. But when you go to the monolayer limit, what you've done is you have a very weak screening here and here, or in other words, there are no carriers there, right? So the only thing, and so this thing is very tightly bound, because the screening is usually what affects your overall Coulomb attraction between the electron and the hole pair, which now is much more tightly bound because your exciton, and hence your exciton is much farther away in energy from the band gap, and it's very tightly bound because of this two-dimensional nature of these excitons. So we have, if you look at its absorption properties, you will see that this coming out, this strong binding energy and the oscillator strength being very large in these materials. In fact, this black line here, this is a figure taken from this paper. This black line here is the absorption of graphene, 2.5% across the entire spectral range. If you take these 2D transition metal dichalcogenides, you will see that the absorption can reach up to about 12% in the monolayer limit at certain specific energies. So at these exciton groups, this comes about because of the d orbitals that are involved in these transitions, which are highly localized, and hence you get these really large oscillator strength. So just to put this in perspective, one monolayer absorbs about 10% light. One monolayer is less than a nanometer thick. It's about 0.7 nanometers thick, to be precise. To get the same amount of absorption in silicon, you would need about 50 nanometers thick, or 50 times the thickness of this monolayer to get the same amount of absorption. So that shows in the inorganic material world, this is, at least to my knowledge, one of the highest oscillator strength systems that is out there. So so they have a very interesting optical property because they can absorb. And of course, from a physics standpoint, they also present a very interesting aspect, which is the fact that these electron hole pairs, as I said, they are like hydrogen atoms. You can have the electron hole pair tied together, and so now you can model them like a hydrogen atom. And of course, with a hydrogen atom, you can talk about Rydberg states, the 1s state, the 2s, 3s, 4s, and so on, where the Bohr radius becomes larger and larger. It turns out that in these 2D TMD systems, you can actually see these Rydberg states, these excited states, all the way up to 5s and sometimes even higher if you apply a magnetic field. And this is something that has not been studied much in other inorganic systems, simply because semiconductor systems, simply because the binding energies are not very high, and so you can't see it. The only system with the exception to this is cuprous oxide, where people have seen it, but there the oscillator strengths are not very large. So how do these systems look? So this is the data, experimental data, that shows how the 1s, 2s, 3s excitons look, and this red line here is a fit to this data, which shows that this fit is it becomes more hydrogen-like at larger n numbers, and it is less hydrogen-like at smaller n numbers. But the most important take-home message from this slide is the fact that the wave functions are now much more delocalized, or in other words, they become much bigger. So the advantage here is when these wave functions become bigger, they can interact with each other much more. It's much more likely that they will interact with each other. So, for example, this one is localized to under about 25 angstroms, whereas if you go to this one, you can get up to 100 angstroms. So you get a much larger Bohr radius, which means they interact much more easily with each other. So the other interesting property of these materials is the fact that all the excitons lie in the plane. So this is an data from photoluminescence, where we've just imaged it in the Fourier plane, and you can see that the emission radiation pattern closely follows what one would predict for a two-dimensional dipole. So the bottom line is that the excitons in these 2D transition metal dichalcogenides really are 1A-like, but with properties that sometimes start to resemble what happens in the case of Frenkel excitons. So this is really a, again, you're getting a best of both worlds type scenario here, where you're getting these large binding energies and so on, but you still have a 1A-like excitons. So just to quickly summarize the reasons why one would want to do polaritons with 2D materials: the binding energy, the large oscillator strength. Because the binding energies are large, you can even get charge complexes called Trions, which are existing in these materials. You can also get Valley properties, which is the fact that you can come with circularly polarized light and excite carriers with specific spin states. I'll talk about that in a few slides. So these are all intriguing properties of 2D materials that makes them unique compared to conventional semiconductors like gallium arsenide or organic materials. The other advantage of these materials, of course, is that you can stack them up. You can use the graphene, you can use the Scotch tape technique to exfoliate them. You can stack them on top of each other. And I often joke that this advent of van der Waals materials and the Scotch tape technique and just buying a crystal and being able to do this has actually democratized this material science world. Prior to this, people would have to rely on growers from certain groups who can grow these high quality materials, and then you get them and then you do it. I'm not saying the growers are not important anymore, but I'm just saying that this allows us to uncover a lot of interesting physics and applications without having to have a expensive growth system or anything like that, like an MBE system, which would cost over $500,000. Here, you just buy the crystal, and then good practice, good hands, you can do this. In my lab, I have even high school students who come into my lab and are able to exfoliate and make these kind of structures. So it's a question of practice more than and patience. So for all the students in the audience, I mean, this is a very encouraging aspect of these 2D materials, that you can jumpstart on this topic much more easily than some other material systems. You can also make heterostructures. You can make structures with different band gaps. You can create carriers in different layers. So for example, here you can create these indirect band gap indirect transitions. So when we started this work back in 2015, we just got, we weren't that good with Scotch tape. So we just got CVD grown materials. We took this material and put them between two mirrors. So this is a mirror, this is a mirror, and then we transferred the 2D material in here. And what you see here is what happens when you go away from this. So you have a flake sitting somewhere here, and then you go to a region that is here, and what you see is that it's just a cavity resonance. And then you go to this region and you get this splitting, or the Rabi splitting that I was just telling you earlier about, and you get this strong coupling. In fact, if you look at this slide here, you will see that you get the typical anti-crossing behavior, and you can extract out the Hope field coefficients and so on. This was work done by my then graduate student Xiao Zhe, who is now a faculty in China. And there has been several other groups that have reported similar work soon after, and it's now become a field that a lot of people are exploring, even with plasmonic systems. So here is an example where people put plasmonic nanoparticles, and then they couple that to photons. The plasmons in the structure were coupled to the excitons, and they were able to show strong coupling in these systems. So the 2D materials presents a nice platform to study strong coupling, simply because the oscillator strengths are large, binding energies are large, you can do it at room temperature. So even with losses in plasmonic systems, you can see these strong coupling effects in these systems. I briefly alluded to the topic of valley polarization. So I'm just going to tell you what it is. It comes from the fact that in these systems, there is a broken inversion symmetry. And so the K and K prime points in your crystal lattice are not in momentum space, are not identical. And so the selection rules of the light are different because of the spin of the carriers that are involved. So if you look here, you have there are two different transitions. So you have the K for the two different excitons. Let's just focus on the A exciton for a second. So you see the A exciton can be excited by sigma plus, whereas here the A exciton can be excited with sigma minus because of the spin of the carriers that are involved. Okay, so here it's both spin up, here it's spin down, and so you can get excite with sigma plus or sigma minus light. The result is that when I come with right-handed circularly polarized light or sigma plus light, what I get out, or the photoluminescence that comes out of the system, is also sigma plus. So here is data from this paper here. They show that if you come with sigma plus light, you get mostly sigma plus emission. You come with sigma minus, you get more sigma minus. So this property is called valley polarization. And because of this property, people also refer to this valley degree of freedom as a valley pseudo spin. So it's like a spin property, and so it's called the valley pseudo spin. What we were able to show was that these polaritons, or these strongly coupled states that form in these systems, also preserves the property of this valley polarization. So we just make a strongly coupled cavity, we study the polariton emission here, we come with sigma plus light, we ask the question, what is the helicity of the light that is coming out here? Is it sigma plus or sigma minus? And we were able to show that indeed they follow the same helicity principle, or the valley polarization property. And in fact, what is interesting with the polaritons is, as you make the polaritons more photon-like, its helicity actually, you can see the helicity actually increases as you go towards more exciton-like at large angles, and then it decreases when it is at zero angles, because there it is very photon-like. And so this was work reported in 2017. There were two other groups that reported very similar work. So the take-home message here is that the polaritons inherit this property called valley polarization. The other interesting property of these systems is the fact that you can make them propagate long distances by coupling them to very photon-like mode. So here we don't even have a cavity. We just have a distributed Bragg reflector. You have a mode that gets created at the edge of this system called the block surface mode. And these block modes can be used to couple to the 2D materials because there's a gradient of the field. And what we were able to show was that, so this is just your strong coupling data, but what we were able to show is that there was when we exfoliated this material, there was a very tiny crack in this material. You can see this in the optical microscope image. But if you look at the polariton propagation, it actually propagates through the system without any problem, because the polariton is very photon-like. It's able to propagate up to about 60 microns in this case without getting disrupted, because it has inherited the property of the photon, and hence it doesn't see these cracks in the system. This was work we had done in collaboration with Stefan Kenner-Cohen and Daniel Sanvito's groups, where we showed this long-range propagation. More recently, we got into the business of asking the question, can we make these systems electrically driven? So this is a very device application that I'm going to show you now, where we wanted to ask, can we make an LED which can, or electrically driven polariton device? So this goes back to one of the motivations I was telling you about, how one can make stack these materials and create all sorts of interesting optical properties, or you can create all sorts of responses from the system. So what is shown here is a device that is made fully with the Scotch tape exfoliation technique. We take so it starts with a hexagonal boron nitride. You stack a layer of graphene, a thin layer of hexagonal boron nitride, tungsten sulfide, another layer of hexagonal boron nitride, graphene, hexagonal boron nitride. If you stack these things up, then the band structure of this material looks like this. You have a graphene, you can apply a gate voltage, you can change the Fermi level, and so now you can make your Fermi level above the conduction band of the tungsten disulfide. You can make here the Fermi level below the conduction valence band of tungsten disulfide. So now you can inject electrons here, you can inject holes here, and the electron and the hole will recombine in the system and emit a photon. So it's an electrically driven device. And in fact, if you look here, this is the IV characteristics, and you can see the IV characteristics have the typical IV characteristics one would expect. Just to show you how this device look, of course, they don't look beautiful at all. These are all exfoliated, so you have no control over the shape of the crystal that you're exfoliating. But you're starting with a boron nitride layer, and then you're just picking up different layers, and then you're stacking them up and creating this completely electrically driven device. To me, it's fascinating that you can actually make a tunnel device with this Scotch tape technique, and it works, and it actually works. So the whole thing is done with exfoliation. The key here is that if you're making an electrically driven device, you need to have it in such a way that there is current flowing through the entire system, which means there needs to be overlap between the different layers. And of course, there are techniques for this, like registering the different layers and making sure that one is on top of each other and so on. So this entire device had about 11 layers inside it, and what we show here is that indeed you can show it to be strongly coupled in white light reflection, photoluminescence. But the thing that you want to pay attention is the electroluminescence. You can electrically drive this device. It shows that it actually emits polaritons, and the polaritons actually follow the dispersion of my the polariton emission follows the dispersion that is expected from this device. So here is the flake. So this is my flake in this device, or the region that is actually overlapping with all the layers. And you can see here, so just to give a perspective, this is about 2 micrometers. This is about 5 microns in length. So that's the area that I'm looking at. So it's not a large device, but nevertheless, you can see that at low current densities versus high current density, the system lights up very bright. This was a really heroic effort, in the sense that it was these 11 stacked layers made and inside a cavity and making it all strongly coupled. And I really owe it to these two guys, Vishwanath, who is now a faculty at IIT Jammu, and Jay, who is now a postdoc at Cornell. These two guys were in my group at that time, and they're the ones who really spearheaded this effort and convinced me that it's worth doing this electrically driven device. So, real credits to them. I briefly mentioned Trions, and I want to just reiterate the fact that the Trions exist. And in fact, people have now been able to show strong coupling to the Trion states as well. And this is a very interesting regime, because now you have coupling to a charged state. And so now, because of the charged state, the interactions are much stronger. And there has been a lot of recent work in this topic of the Trion polaritons. I'm going to spend a little bit of time now on how to push this into the quantum regime, or is there an avenue to do something fun from a quantum standpoint? And because everything that I talked about so far is all classical, in the sense that you're getting coupling between ensemble of excitons, and they're all emitting a photon or several photons and so on. But now you can ask the question, what happens if I go down to the few photon limit? So in this case, I come with one photon, I create one polariton. If I do the calculation in the not the Jaynes-Cummings model, but what is called the Travis-Cummings model, where you incorporate the interactions of the particle, then you will see that as I go to the second polariton, two polariton state, because of the interactions, the energy level associated with this two polariton state is different from the energy level associated with one polariton. In other words, if I have two polaritons in the system, the energy spacing between the upper and lower polaritons is different compared to what it was if you had one polariton. And this shift is coming about because not because I have increased the number of oscillators, but which also happens, but that is different from what I'm talking about here, because what is really happening here is I take my cavity photon, I get a polariton state, I introduce more excitons into the system. The exciton-exciton interaction between the system essentially creates a net shift in my exciton energy, and that comes about because I have changed my because of the dipole-dipole interaction. I've renormalized my exciton energy level. I shifted up, and because of that, now I have shifted all the energy levels up. So if I sit here and I watch what happens, I see that if I increase my exciton density, it has moved up, and this is what I was telling you about the shifting that in the previous slide. Of course, there is another effect that can also happen, and as it turns out, what we have figured out is that in the 2D TMDs, this is the effect that seems to dominate, where as I increase the exciton carriers, because the excitons start seeing each other, I start getting a phase space filling effect, and so my Rabi splitting starts decreasing. So, so this is where the Rydberg states come into picture. So it was, theoretically, it has been shown that the nonlinearity, if I go to these larger n Rydberg states, then I will get increased nonlinearity. So we wanted to explore this property. So we went back to the 2D materials, and it turns out the interaction strength is proportional to square of the Bohr radius. So we wanted to ask this question whether it is indeed the case. So we went ahead and made a system, and the question we were asking was, do the interaction strength of the 2s exciton, for example, scale with the Bohr radius? And so what we did was we made a cavity, again, work led by Jay here, where he made a 3-layered stacked system and then encapsulated between boron nitride, cavity covered with a silver layer on top. The theory for this work was led by Thomas Pohl's group at Aarhus, and we had collaborators from Tony Hines and Jim Horn's group at Columbia, as well as Stefan from Montreal. And what we see here is that as I go to lower temperatures, you get the strong coupling effect. But what is most fascinating about the system is as I go to higher densities, the 2s state seems to saturate much faster, or seems to undergo a bigger shift compared to the 1s state. So pay attention to the density of the carriers that are involved to shift your Rabi splitting by the same magnitude. You will see that the interaction strength is about 4 times the interaction strength of the 1s exciton, and that goes with the fact that the Bohr radius is actually scaling by the same value. So this was a very promising result that you can go to these excited states of Rydberg states, and you can get. And so this is actually the first time the Rydberg states in 2D in solid state systems have been used. They have been used in cold atom back systems for a long time. People have been using Rydberg states for blockade and so on over the last 10 years or so. But this work really shows that you can extend this to the regime of solid state systems, or it has to be at low temperature. So these experiments were all done at 4 Kelvin. The last topic I want to kind of briefly discuss is this idea that you can actually create polaritons without any cavity in these systems. And this is, to me, is very interesting because you don't need to make a mirror or anything like that. So this is not in the monolayer limit, and that's a key aspect. You have to do a few layer system, so it doesn't emit light. Nevertheless, it still absorbs light. But if you create the thickness of this layer to be the right thickness, then what happens is you can create a Fabry-Perot mode between these two interfaces, and you can get the light to get trapped inside the system, and essentially it forms a Fabry-Perot resonance. And what you will see is that once you look at the system, because there are excitons in this system, if I couple that excitons to this mode that gets trapped inside, I can get the typical Rabi splitting property. So what we did was we made such a system. We made a bulk material. So it's just a bulk material. And this is dispersion. On right is simulation. This is simulation. This is experiment. You can see the Rabi splitting. We know that there is strong coupling in the system. There's no cavity involved. But what was most interesting to us was when we did, we were doing these experiments to study the second harmonic generation. So typically what one would study in your textbook is, if I take a bulk system and I do my second harmonic generation, I should not see any second harmonic generation because it's a bulk material. And in this bulk material, centrosymmetry is not broken. So you need non-centrosymmetry. Now, of course, people would have seen it in the surface effects. But so the first question we ask is this a surface effect? And so the first thing we see is that you can take the same bulk material and shift it away from the polariton resonance, and there is no second harmonic generation. So you only get the second harmonic generation if I am in resonance with the polariton mode. And it shows the typical quadratic dependence on power. This work was led by these two graduate students, Mandeep and Razlan, and it was last year's Clio. It was a post-deadline paper. So we went to our theory friends, Andrea Alu's group, and we tried to understand what's going on here. And as it turns out, it can nicely come out from your electromagnetic modeling, where you see that when you are in the strong coupling regime, each of the layers sees a slightly different electromagnetic field, and hence your although the whole bulk is centrosymmetric, the fields don't cancel out because of the phase accumulation at each layer. And the result of this is that if you take a bulk material in a polariton regime, you can get a large increase in the overall second harmonic signal. So in some sense, what we have done is we have relaxed the rule for nonlinear optics through the strong coupling, where the strong coupling or the field associated with strong coupling essentially changes the phase accumulation at each of these individual layers. And so these layers act as if they are individual systems, and they add up to give you a net second harmonic signal. I must point out that what you get from the monolayer is actually, although the theory shows that it is lesser, experimentally what we see is that it's actually slightly better in the polariton case than in the monolayer, at least at low power levels. So I'm just want to conclude by saying that there has been a lot of work. How much time do I have?
So 10 more minutes.
Okay, so I'm just going to ongoing work. We are trying to do condensation of polaritons at low temperatures. We've got some evidence of things condensing, getting to K equal to 0, but one of the big bottlenecks we are having is the fact that there are trions in the system, and we are trying to address these problems with this. But one promising aspect is that if I look at the intensity at K equal to 0, which is blue, it increases at a rate that is at a slope that is higher than the slope at K equal to 20. So which means that there is more polariton scattering to K equal to 0. So we are in the right direction of getting some condensation effects. So I think I'm going to briefly mention this, that this is not much of work that we have done, but phonon polaritons are also very popular in these systems. Since I'm talking about polaritons and van der Waals materials, I just wanted to quickly mention this, that materials like hexagonal boron nitride host phonon polaritons, and these phonon polaritons have this property that they are anisotropic because the dielectric constants parallel and perpendicular in these materials have opposite signs. And so I'm going to just skip to this idea that if you take these materials and you look at their resonances at certain specific frequency, you will get this hyperbolic dispersion in this material, and they are naturally hyperbolic. So I'm just going to show you what happens in hexagonal boron nitride at these mid-infrared wavelength ranges where there are phonon frequencies. You get this hyperbolic dispersion because you see here the dielectric constant is negative for one. Let's take the real part and parallel part. So the real part is positive and the parallel part is negative. So you get a hyperbolic dispersion in these systems. The same thing happens here. You get the opposite signs at another wavelength range. This is the hyperbola of one surface, hyperbola of two surfaces. So these are naturally hyperbolic metamaterials. And the nice thing about them is you can now make all sorts of interesting properties, like making cavities that are sub-wavelength. And in fact, they've shown this. You can make a boron nitride cavity that is sub-wavelength because you are not limited by the largest wave vector that you can excite in these systems. and you can get propagation of phonon polaritons over long distances. And you can see here that you can propagate up to 8 to 10 microns in these systems. Again, the key here is that these are all in the near infrared part of the spectrum. People have made resonators, and you can see here compared to a gold resonator, the HBN resonator in the mid infrared has a much higher Q value, which is a good sign, especially if you want to do couple these to molecular vibrations and so on. So again, the other intriguing property is that because these have hyperbolic dispersion, you can study their, you can look at their these systems in the subdiffraction limit. So you can see here that these systems are, these disks are much smaller than the wavelength of light that you're looking at. Despite that, you can actually see these things when you excite the phonon polaritons because of this trajectory of the rays that happen in these systems, and you can break the diffraction limit. So there are also plasmons in these systems. So there is a lot of work on plasmon polaritons in these systems where people have looked at graphene. In fact, there's a very recent work where they showed very strongly confined plasmons in these systems because graphene is just one atom layer thick, and so you can get very tight confinement in these systems. So this is just a quick overview from an article by Tony Lowe and co-workers where they showed that in these systems you can get plasmons of different in different materials, say, or plasmons with different properties, but most importantly the damping is very different from different materials, and in fact in some cases you can even get damping rates that are lower than typical gold films and so on at some wavelength range. So just a quick outlook on where things are headed to. There's a lot of excitement about these 2D materials from the context of twisting them and creating these moire patterns and the physics of what happens to excitons in these moire systems, and coupling them to cavities, of course, then in which case you have a lattice of excitons coupled to cavity photons. There's a lot of there's also interest in whether you can engineer the phonon modes. So if you take two of these materials and stack them up, the phonon modes start interacting, and that should change your overall phonon response in these materials. So you're creating a phonon superlattice in some sense. The plasmon polaritons, people have studied plasmon polaritons with in hyperbolic plasmons, in anisotropic boron black phosphorus, and chiral plasmons into gapped Dirac materials and so on. So I think what I'm trying to get at is there is all these new emerging quasi-particles that one can see in these 2D materials, and 2D materials really are a very nice platform to study a whole class of these hybrid quasi-particles, which previously would not have been possible with one single material class. There has also been predictions of Cooper pair polaritons and magnon polaritons in these systems with various classes. So this is with superconducting materials, and this one is with this was more of a theory paper which talks about where you could see these in some magnetic materials. So I guess I want to conclude going back to this slide. You know, you have all these states, these quasi-particles that have been shown by now, and there are new emerging quasi-particles that people are looking at to see if we can see them. And this 2D material essentially presents a nice platform to study these properties. So with that, I want to thank you all. The team that has, of course, made it all possible. My group here, this was pre-COVID days, and all the students who made this possible, Jay and Vishwanath, who led most of the 2D TMD work in the early days, and then Mandeep and Resland, who have been leading it now. We have some work on organic materials led by Sitakant, and perovskites by Prathamesh, and we have some other areas that we work on as well. So with that, I'm going to leave you with these recent publications. I want to take a minute and quickly advertise something. I'll go back to the publication slide in a second. We are also part of, there is a whole photonics initiative at CUNY, and I just wanted to mention to all the students in the audience that there are opportunities for everything from project visits to graduate students to postdocs here. Between all of us, some of the names you might recognize in the field of photonics, and we all interact very closely with each other, and we've built a photonics program at CUNY, which is now considered to be a reasonably strong program. And so I encourage all of you to get in touch with me if you have any questions about the program, or if you want to apply to anything with all of us. And so with that, I'm going to stop, and here are the relevant publications on the topics that I discussed today, and happy to take any questions.
Okay, thank you, Shiv. So now QA session is open. It is requested to audience, please post your question in QA box. So we have a couple of questions in QA box. You can address it.
Okay, let me just open the QA box. So the first question is, what parameters should we take care during the exfoliation of monolayers? Does substrate matter, and what kind of cleaning and how much clean lab required for exfoliation? Should we need any glove box kind of thing? So I'll start from the bottom. We don't need a glove box for most materials that we work with. In fact, all of these experiments that I showed you today, none of them were done in a glove box. They were done in the ambient. Important thing is that we've learned is that we need to encapsulate the 2D semiconductors like tungsten disulfide and so on between boron nitride layers, and that essentially ensures that these materials are have good optical responses. Substrate cleaning does matter. You can find the substrate cleaning recipes in some of our papers on how it is done, and the key here is that you need to have substrates that are, of course, clean, but again, like I said, you can do it in ambient environment. These materials don't stick to all substrates. So for example, recently we found that it doesn't stick to chrome very well, but it sticks to things like silicon dioxide very well. So most of the time the substrates we use are thermally evaporated silicon dioxide on top of a silicon substrate, and then we transfer the 2D materials on top of that. Question 2, can we do switching of WS2 based devices? What could be the possible modulation frequencies? So the first question, that's a good question. So there has been some recent work where what they've done is to take a 2D material like tungsten disulfide, and let me see if I can write here. Yes. So what they did was they took a 2D material and they put it on top of a ring resonator. So they just put it here, and then they shine light here, and they look at the light that goes out and comes back, and they looked at the transmission of the ring resonator. And what they did was to modulate the dielectric property of this 2D material. So this was a monolayer semiconductor that they, or I don't remember if it was monolayer or bilayer, but they modulated the dielectric property of this material. But what was interesting about this result was they did not modulate this. They were operating this device in the infrared. I don't remember if it was 1300 or 1550, but they were operating in one of these infrared, near infrared windows. But you know the exciton resonance of these materials is in the visible. So even far away from the exciton resonance, they were able to introduce enough phase change that you were able to go through this. And the exact switching speeds, I don't remember, but this is a paper from Michael Lipson's group where they were able to show, the first author is Datta, and it's a Nature Photonics paper from 2020, if I'm not mistaken, where they were able to show really good switching. Can you please explain the physical origin of trions? So you can have electron hole pairs which are tightly bound by the Coulomb attraction, but you also have extra electrons floating around. And now it turns out that you could make a 3-body complex out of these things, because this electron is also attracted to this hole, and you could create, and whereas these guys are repelling each other, and so you could create these 3-body states. But because the electron hole binding energy is so large, you could still get away with creating these trion states which have got an extra electron. And of course, I'm not going to go into the details of this. Electron can come from another valley and so on and so forth, but let's just think that you can create, they form. But because the binding energy of the electron hole pair itself is on the order of hundreds of MeV, you can get 300 MeV, for example. You can get the trions to have a binding energy on the order of 30 millielectron volt. And so that's still about room temperature, and especially if you go to low temperatures, you can have them. So that is, what happens with trions, and that why trions can exist. They of course have a lower oscillator strength as well, so it's not easy to couple them to cavities. You have to go to low temperatures for that. Okay, so the next question. First of all, my question is, recently some groups have reported the negative valley polarization in TMDX. What could be the reason behind negative valley behind it, other than the interlayer exciton? So the only ones I can think of is the interlayer excitons, where the valley polarization should flip. But I should also point out that in second harmonic generation, also it flips the valley polarization, because now you have a 2-photon process that is creating this. And so you're when you emit with a circular-handedness that is of the opposite polarization. So I'm not very familiar with the work that you're talking about, but definitely the interlayer has that property, and also the second harmonic signal also shows this opposite valley polarization property. The other question, how do you make sure exfoliation of heterostructures are stacked up properly? Well, like I said, the way to do this is you can put markers on your wafer, on your substrate, and make sure that your first wafer is sitting here, and then you align it with the next one comes down. You make sure you align it with respect to this layer on the bottom. Of course, this gets more complicated. If you just want to make heterostructures, it's one thing. But if you want to make heterostructures where the twist angle or the alignment between the layers becomes important, that is not easy. Because then what you need to do is you need to make sure that the orientation of one flake with respect to the other flake is precise. So you want to get these angles correct. And that's a little bit more trickier. In fact, the way people do it is you take a monolayer, you do a second harmonic generation, and when the monolayer shows very strong second harmonic signal, and you will get the crystal orientation from that, because such a structure will show some kind of a 6-fold. If you do a polarization resolved second harmonic signal, you'll get a 6-fold symmetry like this. And then from that, you can map the crystal orientation of the or the orientation of the crystal. Now you can take 2 of these crystals, and then you bring them next to each other, and you can do alignment. So there's a whole business in this twisting. People are interested. All of this started out because back in 2018, there were these 2 papers where they showed that if you take 2 graphene sheets and you twist them by a small angle, the magic angle of 1.1 degree, you end up modifying that net band structure of this whole system, and you get these highly flat bands where the interactions become so strong that you can get superconducting behavior. So such emergent properties that can come about just by taking 2 2D materials and stacking them is fascinating. And so there's a lot of work in the context of 2D TMDs where people are trying to do this. And there you need to get your orientations correct and the twist angles correct. And so that's, there's a little bit of work, details on those papers, but there is also more recent review articles that discuss how this twist angle can be controlled. I think I have answered all the questions. Are there any other questions? Or
so I requested to audience, is there any question, or we have a time you can directly interact with our both of the professors?
Thank you all. If there are no questions, then thank you again, and wish you all a happy Day of Light, International Day of Light. And I hope to visit you guys some point. And if any of you are interested in the work we do, feel free to get in touch with me. Thank you all.